Hello, everyone. Although you might not be able to see me so brightly, but I just wanted to mention that in today's class, we'll be considering some further topics. And in those further topics, we'll have things like photoelectric effect, X-rays, and then conduction of electricity in gases. So we're going to dive in almost immediately, and then I'd have you pay rapt attention and be with me. Here we go. Further topics. The first one we'll be looking at today is photoelectric effect. Now we'll start by saying when light falls on a metal surface, electrons are emitted. This process, let me come down here. This process is called photoelectric effect. Emission. Let me put a full stop there. Make it clear that the emitted electrons are known as photoelectrons. Maximum kinetic energy of the photoelectrons are independent of the intensity of the incident light, but depend on the frequency or wavelength of the incident light. So the whole idea here is, we said, photoelectric effect is the emission of electrons when light falls on a metal surface. So let me give it to you proper like that. Photoelectric effect is the emission of electrons from the surface of metals when light falls on them. That's just like a proper definition. That definition was cut from like the first set of statements. So we're already told that the emitted electrons are known as photoelectrons. And they now establish something very clear to us. This is how to read. You go back and start looking at the most important point. The maximum kinetic energy of photoelectrons is independent of intensity of incident light. So it does not depend on intensity. So it's one of the factors that the maximum kinetic energy does not depend upon is intensity. But we're told that it depends on frequency or wavelength. So it depends on what? Frequency or wavelength. So please take note of that. It does not depend on intensity or depends on frequency or wavelength. Take note of that. Now we go further to discuss some other things. Let me see if I can describe this diagram right here. So I have a diagram that like tries to express the concept of photoelectric effect. Let me use this. I have an ammeter. For an ammeter, I just prefer to write it as write that A. Now I have a tube. In that tube, I have one electrode. I have another electrode. I call this electrode. Okay. Let's just go on and draw the diagram simply first. I have voltmeter here. And then this goes up to a point where we have something like this connected to battery, where this is the positive and negative terminal. So this junction where this touches this, they call it C. With this, I've connected this and give it a touch here. So besides that, positive, negative, meter, positive, negative. Oh, this is the diagram we have in question. So light comes. Let me do that again. Light comes and strike this one, and then we call this the evacuated tube. These guys are the electrodes. Electrode. We know obviously this is an ammeter, this is a voltmeter. So let me erase those arrows. We already know that. So this is just an idea of what it means. You strike, the surface with light, and electrons are released. Now, this is the direction in which current will flow. So this is just a diagram that typifies that. I don't necessarily think it's a good idea to memorize diagram, but we'll continue in our explanation just to have a visual picture of a setup. But then it might not be too important. So let's continue with our discussion. Increasing, when I say too important, I mean at this level. Increasing the intensity of light increases the number of photoelectron, but does not increase the energy or velocity. The absorbed energy is used to overcome potential barrier of the photoelectrons. So we have made it clear that increasing intensity will increase number of photoelectrons. To increase intensity, you increase number of photoelectrons, but does not increase energy or velocity. So absorbed energy is used to overcome potential barrier of photoelectrons. So keep that in mind. Let's go to applications of write this in black. Applications of photoelectric effect. Some people just call it photoelectricity sometimes. Let me shift it to this side. Electric emission is used in the following. Number one, we have burglary alarm. Television camera. Automatic devices. Or switching light at docks. Street light. Sound production. Industrial control. Industrial controls and counting operations. So these are the uses of photoelectric effect. Einstein photoelectric equation is what we're looking at next. Einstein photoelectric equation is what we're looking at next. So Einstein photoelectric effect is given by this particular one. So I decided to give the notes for a while before now speaking about it. Now, we have started defining the terms. We said W there is equal to this, so we can easily write E as what is that closely? That's another way of writing E. So where E is maximum kinetic energy that is given to photoelectrons, W is work function, we call the work function, and then F naught is threshold frequency. We have then HF itself, where we have F is the normal frequency given, it's just frequency, while HF is like the energy of liberated electrons. So we get to see the difference when we are working more with questions. Okay, let's now define some terms like threshold frequency. This is the lowest frequency that can cause photo emission of electrons from a metallic surface. Low threshold frequency emission will not occur. So this is the lowest frequency that can cause photo emission of electrons from metallic surface. The idea is that if we have a metallic surface now, there is this frequency where as light is striking this metallic surface, there is a frequency where it needs to get to that will now make, electrons to start coming out. Electrons will be emitted. So, but if it doesn't get to this particular frequency, there will never be the emission of electrons. So that's why he says it's the lowest frequency that can cause. So it's the minimum. If anything is less than it, if you have another frequency, let's say the threshold frequency of this scenario now is like maybe 5 hertz, and this light that is coming struck it, and the light got to a frequency of 4 hertz or even 4.9, electrons will not emit from this surface. Electrons will not. Until you get to 5 hertz before you can now start to see even the first electron. So that's the idea. That's what threshold frequency means. That's like the threshold. Even in normal English, you say that's the minimum. Like your jam score now, they say that's the lowest you can get to get into school. So don't get below that. You're not, you understand? That's what they mean. So now, work function. Let's talk about work function. Work function. This is the minimum energy required to liberate electrons from a metallic surface. Minimum energy required to liberate electrons from a metallic surface. So we have minimum energy to liberate electrons from metallic. Let's start taking some examples. Or let's talk about threshold wavelength. There's also something called threshold wavelength, and that's like from, you can easily get that from threshold frequency, threshold wavelength. You will see how we can get that. Or we'll start taking examples. This is the longest wavelength that will produce photoelectrons when the surface is illuminated. So we have W equal to, normally this is like work function now. And then we know that frequency is always equal to C over lambda. So in this case, F naught will be C over lambda naught. So you see this lambda naught now. Lambda naught is C over F naught. We can write in another way by saying H equal to W equal to HC over lambda naught. And then we can write lambda naught as AC over W. So we have this. Very good. That is the whole idea. So let's go to answer questions. Compute the frequency of the photon whose energy is required to eject compute the frequency of the photon whose energy is required to eject the surface electron with a kinetic energy of 3.5 times 10 raised per minus 16 electron volt, or 3.5 times 10 raised per minus 16 electron volts if the work function of the metal is 3 times 10 raised per minus 16 electron volts. And they gave us some of this stuff as H equal to 6.6 times 10 to the minus 34. Those are constants. They gave us 1 EV equal to 1.6 times 10 to the minus 19 joule. That works. The frequency. What are we looking for? Frequency. Whose energy of a photon, whose energy is required to eject a surface electron with a kinetic energy of, now they just gave us the kinetic energy. I'm going to explain some things to you. Give us the kinetic energy. If the work function, now give us work function. If you go back to this formula over here, you look at it, this particular one, I'm going to point at it, this one. In this formula, E is kinetic energy. Take note of that. HF is just, call it like the energy of liberated photoelectrons. Then W is work function. If we bring that idea of the formula here, we can write it as E equal to HF minus work function. So basically, they just gave us E, kinetic energy, 3.5 times 10 raised per minus 16 equal to HF minus work function, 3 times 10 raised per minus 16. Now get this straight, that all these things were given in electron volt. Electron volt. All these energy. So let's quickly convert them to, before we use the formula even, let's convert them to joules. So in order to convert them to joules, we know that 1 electron volt equal to 1.6 times, and that was given to us right here in constant, times 10 raised to minus 19 joule. Let's convert the kinetic energy. We now know that, okay, 3.5 times 10 raised to minus 16 electron volt equal to x. If we cross multiply, x equal to 1.6 times 10 raised to minus 19 times 3.5 times 10 raised to minus 16 electron volt. And that will give us this is kinetic energy. Don't forget that. So let's do the same thing for the work function. 1 is equal to 1.6 times 10 raised to minus 19 joules. So the work function of 3 times 10 raised to minus 16 will be equal to x. And when we cross multiply, x will be equal to 1.6 times 10 raised to minus 19 times 3 times 10 raised to minus 16. So that will leave us with uh, 1.6 times 10 raised to minus 19 times 3 times 10 raised to minus 16. 4.8 times 10 is per minus 35. And that's joules as well. So now we can now go back to our formula. E equal to HF minus this. And we already have our E as 5.6 times 10 raised to minus 35. Then equal to HF minus 4.8 times 10 raised to minus 35. So going on with that, we have 5.6 times 10 raised to minus 35 plus 4.8 times 10 raised to minus 35 equal to HF. So establishing that, we have 1.04 times 10 raised to minus 34 equal to HF. Now, what is the goal of this question? We want to find F, right? So H is already given to us as a constant. What do we simply have to do? Plug it in. So F will now be 1.04 times 10 raised to minus 34 over H. So, but H is equal to 6.625, I guess. That's up there. Or let's say 6.6. The constant given to us here was 6.6 times 10 raised to minus 34. So let's use it that way. 6.6 times 10 raised to minus 34. Just seconds. So we just plug it in there. F will now be 1.04 times 10 raised to minus 34 over 6.6 times 10 raised to minus 34. And that leaves us with a frequency of let me do this, divided by 6.6 times 10 raised to minus 34. That leaves us with 0.157 hertz. That's the answer. Let's go to another example. They said that the working frequency of lithium is, hold on for a bit. The working frequency of lithium is 2.30 electron volt. That's what we're told. Calculate the maximum energy in joules of photoelectrons liberated by light of wavelength the threshold wavelength of the metal So now, yeah, those are that's the question, and yeah, to find out how we resolve this. Now we must first establish what is working frequency. Working frequency is work function. Let me establish that quickly. When you hear a question say working frequency is work function. So digest that first. That working frequency is work function. Keep that in your mind. Working frequency is work function. So working frequency is work function. Let's utilize it. So I'm going to write in this question. They said the working frequency is 2.3 electron volt. So the easy thing for us to do is convert that to joules. Remember, the 1 electron volt is 1.6 times 10 raised to the power minus 19 joules. Then 2.3 will be x. X will be 1.6 times 10 raised to the power minus 19 times 2.3. So we have 3.68 times 10 raised to the power minus 19 joules. That's our answer. So now we are given this working frequency, we've converted it to joules. One has to find the maximum energy in joules of the photoelectrons liberated by light. You know what they're asking right now? Maximum energy. When you see maximum energy, it is still talking about this guy. This guy here. Maximum energy to liberate, to make that liberation occur. We're already given like to make that photo, the maximum energies in joules of photoelectrons liberated by light of wavelength. They have given you a specific wavelength. So they gave you, and how we will analyze this. This is maximum energy we're looking for. Let's proceed. We have H. I've told you F can be written as C over lambda, then minus W. Then we already have lambda. They gave it to us in that particular question. They gave it to 3.3 times 10 raised by 17. 3.3 times 10 raised by 17 meter. Settled. So we can now plug it in. We're looking for maximum energy. We can now plug everything in by saying 6.6. What did they give us as H in this question? Don't worry, we already know H. They gave us from previous ones. So let's use 6.6 times 10 raised by minus 34. Then times C is 3 times 10 raised by 8. That's C. Lambda is 3.3 times 10 raised by 17. Minus work function that they gave us, 3.68 times 10 raised by minus 19. So if we calculate properly, let's calculate this entire guy. Let's see what it gives us. 6.6 times 10 raised by minus 34 times 3 times 10 raised by 8 divided by 3.3 times 10 raised by 17. That will give us 6 times 10 raised by minus 43 minus 3.68 times 10 raised by minus 19. So this is the idea. I think there is an issue here. Okay. The stuff given to us was minus, was it 17 or minus? It's minus 17, sorry. Forgive me. This was minus 17. The wavelength was minus 6 by minus 17. So let's correct that. Minus 17, yeah. So that makes a lot of changes to most of the things we wrote here. That wavelength is like 0.3 times 10 raised by minus 17. Not 3.3 times 10 raised by 17. So let's calculate. So that step will be 1.98 times 10 raised by minus 25. And then 3.3 times 10 raised by minus 17. 3.6, 8 times 10 raised by minus 19. So let's continue to the first part. Divided by 3.3 times 10 raised by minus 17. Okay. That gives me, yes, that's what it gives me. Of course, so that leaves me with 6 times 10 times 10 raised by minus 19. Okay. 6 times 10 raised by minus 9 joules. So now the other part of the question said to find the threshold wavelength of the metal. Now, when we want to talk about that, we're like, okay, threshold wavelength, you can get that from threshold frequency. But how do you get threshold frequency first? We know that the work function is the one that is equal to, we go back to our note. See it right here. Work function is the one that has relationship with the threshold frequency. And then we now said, okay, what function will be hc over lambda naught? So lambda naught, which is the threshold wavelength, is easily going to be hc over work function. So what does that mean for us? 6.6 times 10 raised power minus 34 times 3 times 10 raised power 8 over work function. What is the work function again? We got it already. 0.68 times 10 raised power minus 19. So that's our last example. Get the idea. Go back to these examples and review and see some of the important things we are doing. And from there, you'll be able to make decisions. Learning is structured. It takes patience. It takes you knowing something for the very first time and then going on. You get that. So keep all of that stuff in mind. Let's proceed to the next part of today's class that has to do with talking about X-ray. X-ray. Let's see, black to black. X-ray was discovered. That's why we titled this class further topics. We'll touch a couple of topics up as far as we can go. X-ray was discovered in 1895 by William Rosen. William Roentgen. X-rays are produced when thermally generated electrons from a hot filament are accelerated through a high potential frequency and focused onto a transgene target where the electrons are suddenly stopped. Okay, so X-ray was discovered in 1895 by William Roentgen. X-rays are produced when thermally generated electrons from a hot filament are accelerated through a high potential difference and focused onto a transient target where the electrons are suddenly stopped. So let's see if we can analyze a complex diagram. Yeah, I believe this is some form of battery with some form of voltage. Then we have something over here. I believe that's electron moving. And we also see something like this. We have this particular this is a chamber. This is a glass chamber, and you have it. It transcends and goes right under the voltage source, more like the battery, something like that. So you just have it this way. Uh, so then You have something like this right here. Let me just draw it entirely, then give it labels later on. So here's what we have. This is shaded. Properly shaded, and then you have this guy striped. There is some sort of stuff that runs this way. Another one runs like this. Uh, you have this guy over here is called the anode. Water comes in through here. I can drift this entire stuff. I can drift it to the left. Water comes in through here. Water comes out from here as well. This guy is called the target. This guy is called the window. So this is what we have for an X-ray setup right now. I mean, diagrammatically, I will have to explain the mode of operation before we can make real sense of this diagram. In the X-ray tube, a high potential difference is applied between the hot cathode Okay, so basically they are saying this is the cathode part. This area is the cathode. I'm gonna call this the cathode. This is the anode. So in between them, there is a high potential difference. This guy. So I'm just asking me to explain. So a high potential difference is applied between the hot cathode and then the anode. Electrons are emitted in the cathode and are accelerated to an extremely high speed. They are abruptly accelerated when they strike the anode. Causing Okay, let me go back and analyze some of these points. That is the electron. Electrons are emitted from the cathode. That's where you see these guys. See these are electrons. So basically, this is the cathode. So you see electron emission in that direction. Let me cancel this arrow, just an explanation. So and I accelerated to an extremely high speed. So that arrow that you see like this one going like this shows that they're moving at high speed. So acceleration to high speed, they abruptly decelerated when they strike the anode. So this area, so you see that this entire thing is the cathode setup. Why this entire setup is the anode. Are you following me? So when electrons strike this target, where they call target, this shaded part, so they strike the anode. Let's continue what we're saying. They're decelerated, and when they strike like that, they cause emission, causing emission of high energy radiation of short wavelength. So that's where you see when they strike this part, X-rays are now come out, X-rays. So when you strike the target, X-rays are released. So let me just label, instead of labeling this window, window is more like, I think this other bigger, oh, that's glass chamber. So I'm going to call this X-rays. So when they strike, X-rays are released. So short wavelength. So the anode, there's this analogy that anode becomes very hot in the process. The anode becomes very hot. So you now see a kind of setup where water goes in to cool it and water comes out. That's what's happening right here. The anode becomes very hot in the process and requires cooling. Cooling genes on the outside of the tube. Take note of that. So that's just a very brief explanation of the diagram, and it explains how the X-rays are formed. We can go further to say, let's talk about energy conversion during necessary production. Energy conversion during X-ray production. So during X-ray production, electrical energy is converted to thermal energy. So during X-ray production, electrical energy is converted to thermal energy. Yeah, and that is in the area where you have high potential difference and then hot cathode. So the high potential difference, I believe, makes the cathode hot. Then when you now have that scenario, electrons are now emitted. That electron emitted, they move. So thermal energy is converted to mechanical energy. Thermal energy now is converted to mechanical energy next. That's when the electrons move. And then particular mechanical energy is the specifically kinetic one. Kinetic energy. And we say it to accelerate the electrons, Then finally, they say the mechanical energy is converted into electromagnetic energy. That's when they eventually move and they strike this target, they release X-rays. So we say mechanical energy is converted to electromagnetic energy. Electromagnetic energy of X-ray. So X-ray. So basically, we quickly just highlight the types of X-rays that we have. Types of X-rays that we have. There are two of them. We mentioned them. We have the hard X-rays and we have the soft X-rays. We're going to mention characteristics of hard X-rays. Number one, high penetrating power. Or ability. Number two, shorter wavelength. Let's say characteristics of short X-rays now. The short X-rays, we have low penetrating power. Then we have longer wavelengths. Quickly, want to talk about hardness as a quality of X-rays. Or just as a concept. This is a measure of the strength or penetrating ability of an X-ray. That's hardness. Intensity is the energy radiated by unit time, by unit area, by the X-rays. So it depends. I'm going to give that a formula immediately on the current of the filament. So since the intensity said, I'm going to call it I. It says the energy per unit time per unit area. So I'm going to just use E over AT area. So it's like per unit area and per unit time. That's the energy per unit distance. So where that's how to extract formulas where I is intensity, E is energy, remember, A is area, T is time, unit time. So it's time. Properties of X-ray is the next thing we'll be going to. Properties of X-rays. Properties of X-rays. Number one, X-rays are electromagnetic waves of high frequency. Electromagnetic waves of high frequency. X-rays have short wavelength. That is an estimated 2 times 10 to the power minus 10 meters. We can confirm that better later. Just know they have short wavelength. X-rays have high penetrating power. X-rays travel in straight line. They are not diffracted by electric or magnetic field. They are not diffracted by crystals. They ionize gases. They cause zinc sulfide to flourish. Here's the idea. Properties of X-rays. Application of X-rays. First one, for examining body to locate broken bones, to detect metals and contraband in the baggage. They are used to detect cracks in welded joints. So they are used to detect cracks in welded joints. They're also used for investigating crystal structure. They're used for treatment of tumors and malignant growth. Then it is used in agriculture to kill germs Let's talk about the hazards. Hazards of X-rays. It causes genetic mutation. It can destroy body cells. It causes leukemia by damaging body tissues. It causes skinborne and cancer. So these are the hazards. These are the bad sides. Precaution. Precaution. Very straightforward precaution. Those who work with X-rays should put on lead coats, and they should always go for regular medical checkup. This is where we end today's class. Then we can meet in our subsequent classes.